Okay, so I know what you guys are thinking. You're thinking, well, this is kind of fun, but I really want the challenging problems. I came here to be challenged, not to do easy problems. Well, what happens when we combine acids and bases? Right? Things will get a little more complicated here when we combine acids and bases. So we've got a couple different types of possible reactions here that we're going to try to look at individually. The first one is what happens when a strong acid reacts with a strong base. So in this case, we've got a certain quantity of hydrochloric acid reacting with a certain quantity of sodium hydroxide. So let's look at that reaction. I'm going to put it a little higher on the page. This is one of the places where I did not leave a lot of space. HCl plus NaOH, both aqueous. Now we should remember, right, this is an acid-base reaction. The product's going to be water, liquid, and a salt. In this case, the salt is the sodium left over from the base, the chloride left over from the acid, and NaCl, of course, is aqueous because it's soluble in solution. Now, when we're looking at a one-way reaction, just to kind of keep things separated from ice chart, I like to call these if charts. Because what we need to look at here is we need to be on the lookout for anything like a limiting reactant that leaves something in solution. So we really just need initial and final here, and an if chart is generally going to be in terms of moles instead of in terms of concentration the way an ice chart is. So what we need to do here is figure out how many moles of HCl do we have, how many moles of NaOH do we have, and how do they interrelate in this particular reaction. So let me see if I can fit that up here. I've got 30 milliliters of my HCl solution, and it's 1 molar. That means there's 1 mole per liter, but a liter is 1,000 milliliters. So I think that's a substitution you should probably be reasonably comfortable with at this point. So 30 divided by 1,000, that would be 0.03 moles of HCl. If I do the same thing with NaOH, 20 mils of NaOH, it's also 1 molar, so 1 mole per liter or 1,000 milliliters, and that would be 0.02 moles. So I start with 0.03 moles of HCl, 0.02 moles of sodium hydroxide, right? So we should recognize HCl is in excess, NaOH is the limiting reactant here. So after this reaction happens, I'm not going to have any sodium hydroxide left over, but I'm going to have 0.01 mole of HCl left over. Now I'm going to make 0.02 moles of water and 0.02 moles of sodium chloride, but we should recognize NaCl is not going to affect the pH of our solution. Chloride's the conjugate of HCl. Excuse me. So there's no backward reaction for chloride that would produce hydroxide ion in solution. Sodium is the conjugate of NaOH, so similar there, not going to have any effect on the pH. This amount of water is not really going to change our overall concentration either, but we will have to worry about this excess HCl that is present in this solution. So I've got 0.1 mole of HCl, so let me jump over to this side of the page. I've got 0.01 mole of HCl. Now, if I want to calculate something like the pH, that I need concentration, right, of H3O+. So that HCl is going to react with water. It's going to be a one-way reaction because it's a strong acid, but it's going to make hydronium and chloride ion. So hydronium, that's where my pH is going to come from. Now this one happens to be all 1-to-1, so there's not really any stoichiometry differences we need to worry about here. But if my 0.01 mole of HCl becomes 0.01 mole of hydronium ion, I can turn that into concentration by dividing by the volume. Right? Now here things can get a little tricky because we're mixing solutions together. I started with 30 milliliters, I added 20 milliliters. That means my volume is going to be 50 milliliters at this point. If you take 50 milliliters and turn that into liters, since that's what you want for molarity, that would be 0.05 liters, which means this is 0.20 molar in hydronium ion. Now, if it's 0.2 molar in hydronium ion, we can calculate the pH by taking the negative log of 0.20 and negative log, answer, negative log 0.2 is 0.69897, but since we have two significant figures there in my concentration past the decimal, I want, or since I have two significant figures in my concentration, I want two past the decimal for my pH, so I'm going to round that to 0.70 for the pH of that solution. Okay, now strong acid, strong base, it's all stoichiometry calculations. That's something we probably could have done back in chapter 3, chapter 4 maybe, to understand the acid-base reaction. But this shouldn't be something that is too taxing for you at this point in your progression through chemistry. Now, there's a part B sort of here, and it's what if we substitute barium hydroxide? So by that I mean, what if we substitute that in for the base? And what we should recognize there is if you substitute barium hydroxide, you're going to change the stoichiometry of the reaction. So it's still going to be water, you're still going to get a salt, but in this case the salt's going to be barium chloride, and since barium's a +2 cation, the formula would be BaCl2. In order to balance the equation, you need 2 moles of acid for every 1 mole of the base. Now, even more relevant here maybe is thinking about what our net ionic equation is here. So the net ionic equation for an acid-base reaction is H plus OH minus goes to H2O. So another way to think about this is we're getting 2 equivalents of hydroxide ion for every 1 equivalent of barium hydroxide that we use in this calculation. So if we reconsider this reaction up here at the top of the page, but with barium hydroxide, HCl plus, well, actually I already wrote it there, so maybe we can just fill in underneath where I wrote the net ionic equation. We start with 0.03 moles of HCl. We add 0.02 moles of barium hydroxide, but because of the 2-to-1 ratio here, another way to think about this would be this is 0.03 moles of H plus, but it's 0.04 moles of OH minus, and that means at the end of the reaction, instead of H plus being left over, it's hydroxide ion that is left over. So this solution will end up being 0.01 moles of hydroxide ion left over. If we divide that again by the total volume of the solution in liters, that will give us a concentration. So the concentration of hydroxide ion now, because there's 2 equivalents of hydroxide in the base, that's now what's left over, that's going to be 0.20. That means the pH would be, POH would be 13.30. No, I'm trying to go too fast. So a good example of what happens when you're trying to go too fast. 0.70 for POH, taking the negative log of 0.2. Subtract that from 14 to get the pH, and that would be 13.30. So this would be a very basic solution here. If we use barium hydroxide with 2 equivalents of hydroxide in each equivalent of barium hydroxide for this reaction. Something you've got to watch out for. Barium hydroxide, strontium hydroxide, calcium hydroxide have 2 equivalents of hydroxide ion. Sulfuric acid, H2SO4, has 2 equivalents of H plus when it goes into a reaction. So you'd have to be aware of that stoichiometry as well.